solve abundant diagnostics, been validated and verified numerous benchmark. It has inner object to handle internal geometry. We implemented implicit algorithm for electrostatic and electromagnetics. It's open source and so can be used for many people. We also have a different code specially designed to perform well on modern hybrid architecture on CPU and GPU and scale well. It's three-dimensional. Could be shared for some users, but not that openly like ADPIC. Okay, next I'll talk about algorithms. So the problem we have, if you have a relatively large plasma, say for 300 millimeter wafer, it actually takes a lot of time to simulate this plasma in 2D and 3D. So what we did in the past, we looked at how to accelerate this code, because traditional codes use explicit momentum conservative algorithm, and it has a lot of limitations on time step and special step. And so you really want to avoid that by using more sophisticated, more advanced algorithm. And so what we did in this paper a couple of years ago, we looked at using direct implicit or energy conservative. So if you remember, direct implicit allows you to have cell size bigger than dB radius and time step bigger than 1 over plasma frequency. And energy conserving doesn't allow you to increase the time step, but allows you to increase spatial scale, which is also important. And you can see here on the plot is kind of speed up versus how much bigger cell size is. And in general, what you see that you have a factor of 5 or 6 speed up, which is important if your simulation runs a couple of weeks. So there is a caveat, which kind of known but forgotten. For especially direct implicit, you may not have a very good energy conservation, and energy may change a little bit every step, but it will accumulate. You may have energy loss, so you may have, instead of heating, you may have actually cooling. And there was a long forgotten work by Bruce Cohen in Ron Cohen, where he showed that you have to keep time step proportional to cell size, which is shown here. What you see on this color plot is energy change depending on time step and special step. And so if you keep them proportional, you get a minimum energy change. And that's one simple way to control the energy in particle cell code. Okay, another important issue kind of forgotten is numerical noise. So as everybody here probably knows, right, in the particle cell codes, you have a finite number of particles per cell, typically from 100 to 1,000. That means you have a numerical noise, 1 over this number of particles per cell, and that noise will produce large fluctuations and shortwave fluctuations. And these fluctuations will have to satisfy dispersion relations, so they will look as real waves. And because you kind of pump up short waves, you will produce a lot of scattering on these waves. And so we looked at that, and we kind of recovered all known but somewhat forgotten result that this numerical noise, because it has to satisfy plasma dispersion relation, act as essentially Coulomb collisions, so very enhanced Coulomb collisions. And the issue why it was forgotten, because most simulations in the past have been done in 1D. In 1D, there is no scattering because it's 1D, and so this effect is not manifesting itself in 1D. But as soon as you switch into 2D, that you'll have a large scattering on numerical noise, which has to be controlled and taken account for. And so one way, simple way to see this, you can load in a uniform plasma with periodic boundary a kind of heaviside like distribution, which is constant as function of energy or velocity, and then there is nothing. And so if you have no collisions, which you, in this particular case, right, no implemented collisions in the code, then this distribution is stable, it should stay stable. But in reality, what you will see, you can do this experiment yourself, it very quickly goes to max value on a time scale about 100 or 1 over plasma frequency. And again, physics and numerics of this have been studied before, but somewhat forgotten. So you can do a calculation that account for scattering on these numerical fluctuations. And again, formulas have been worked out a long time ago. You can calculate, and you can calculate rate of this scattering. And so this there was estimated by Hockney a long time ago that this scattering rate is scaled as or time was 1 over plasma frequency times number of particles, macroparticles per cell, sorry, per Debye radius. And typically what you'll see that for most cases, this is much faster than any collisions. And so it's very hard to remove this noise. And so one way to do it is to artificially, for example, increase Debye radius or increase cell size using, for example, energy conserving, and then that will reduce numerical thermalization. But again, in real problems, it's very hard to avoid, and that's something which people have to be aware of. Okay, so now we have codes. What do we do with it? So for one example, which we did a few years back, is look at electron beam interaction with plasma. So this is well-known classical physics. So when electron beam goes into the plasma, it could excite two-stream instabilities and then scatter on these waves and produce plasma. So this very important process in atmosphere, but also this kind of discharges been proposed to be used for plasma processing because it can produce a very uniform large-scale plasma with good controls. So on top you see schematics, on the bottom a real experiment, photograph of real experiment. And typical parameters beam about a few kilovolts, but it will produce a very quiet plasma with a typically density 10 to the 11, beam densities from 1%, about 1% of this plasma density, and it create a very small temperature, which is very good for gentle processing on atomic scale level, which is what is important for modern microelectronics. But as I mentioned, it produced two-stream instability, and so depending on parameters, you can have secondary nonlinear effects, which is, again, I don't have time to go through details, but who is very interested, we recently published PhysRef and PhysRef-E, and so some of the effects have been known, like parametric decay instability or standing wave modulation instability, and so his schematics showing which regime do we get as function of beam density ratio, beam density to plasma density, and electron beam energy to electron temperature. And so you can see this schematics, different regimes you can get of nonlinear interactions. What surprised us at certain conditions, very high beam energy to electron temperature and beam density to plasma density, we get a new regime. We call it electron modulation instability, where you have such a strong linear waves, and these linear waves produce a very large pandermotive pressure pushes electrons away in such a scheme that it violates quasi-neutrality. So again, there was a studies in 70s of this so-called linear collapse, and our contribution to this old story is that at very high amplitude of plasma waves, you produce this kind of new exotic, not that exotic, but new regime. So point is, you can always discover new things in kind of old, well-studied subjects, as you will see in few slides. Okay, now moving to more complicated things. If you have a magnetic field, as everything, with a magnetic field, everything becomes much more complicated. And so magnetic field often used to control this electron beam propagation. So we have electron beam-generated plasma in PPL. It's essentially it's a panic discharge where electron beam goes through the plasma, but then if you drive the current across, um, then you produce electric field, and that electric field has to drive electrons across magnetic field. And so because you have to drive electrons across, ions are confined, and then it's kind of like a trap for ions. But if you have electric field across magnetic, you produce drifts, and that drifts typically unstable, and you produce a lot of instabilities, so-called Simon-Hoe instabilities, and that creates so-called spokes and a lot of nonlinear processes. I know in India there was similar studies with linear machines. Linear machines slightly different physics because in linear machines ions are magnetized. If ions are not magnetized, the physics changes. And there is a similar linear machine in Mistral where they also study this basic phenomena and look at waves and turbulent transport. So we also kind of revisited this configuration. uh, Having our 3D code, we can simulate a relatively large box, which is shown here. This is 20 centimeters by 2.5, and we inject electron beam in the magnetic field and basically see what happens. Um, and so, yeah, this is a movie, and you can see that on certain regimes, uh, this plasma produces this kind of complicated helical structures, which rotates. And again, don't have time to discuss all the physics, but it's basically centrifugal instability which drives this self-organization. And again, this point is that with 3D code, you can discover new physics because, yeah, otherwise it's very hard to understand how plasma self-organizes in 3D. Okay, now switching to a little bit more simpler physics. So for industry, capacitive discharges is bread and butter for processing devices. And again, because it's so simple, seemingly simple, right? It's very well controlled. And so what you do, you have basically a couple of electrodes, you produce, you apply RF voltage, and you produce plasma. If your voltage is about kilovolt, you accelerate ions, you have ion energy about kilovolt. This is needed for high spectral ratio etching. And because you can control it very well, you can change the waveforms in capacitive discharge and have a very absolute control on, very precise control on ion fluxes and radical fluxes. And that's basically what industry needs. On the right is again a photograph. And so what's so special about these discharges is that for typical conditions of low pressure accumulator, if you measure electron distribution function, which is shown on the right, it actually very non-Maxwellian, and the shape of distribution function can change from this kind of distribution function with a lot of cold electrons, with a completely opposite case at high pressure. And so people looked at this, trying to understand what forms and why, what's the reason for formation of this non-Maxwellian distribution function. And one of the reasons is so-called collisionless heating, which is old paper about 50 years ago by Valery Gadyak. He is experimentalist, he measured things, and he asked himself question, what determines power deposition in this system? And so he measured power, he measured currents, he measured density, and then he looked at kind of effective frequency where you take power deposited and divide by essentially ohmic-like quantity, current density squared, length divided by density. And so if it's simple collisional heating, it essentially should be collisional frequency. But what he found when he plotted it with measured effective frequency as function of pressure, that at low pressures, this frequency is much larger than collisional frequency. You can see it's like 30 times bigger. And it scales essentially like thermal velocity due by length. And physics explanation, again, kind of been well known. So it goes back to Fermi proposed acceleration mechanism. So essentially, sheath, you can look at a ref sheath as essentially kind of moving head wall, which moves back and forth, and electron collide with it and pick up or lose velocity. But in average, in that process, you gain energy. And so you can show with a very simple trivial calculation that in average, you can gain energy and scale it with a collision frequency with this hard wall. So this is very simple physics. And again, to our surprise, we kind of revisited that and we see some new effects, which Sarvish will tell you. Now, for control of these ref discharges, some years ago, people tried to use a very weak magnetic field. So if you apply just a few Gauss, maybe 10, 20 Gauss magnetic field, you have a lot of control of these discharges. And one way to do it is, for example, so what you see here, it's a coils, and they have a current and produce a magnetic field. So this magnetic field will be parallel to the this is on top you see electrode parallel to the electrode. But the problem, if you have just fixed magnetic field, you'll have a drift and plasma will become non-uniform. So one way to mitigate it, you can rotate this magnetic field and you can control uniformity that way. And so what we looked at to understand, we with Cyrus group, we studied how this small magnetic field will change plasma parameters. And again, this is our recent papers. And as you can see, so this is density versus magnetic field as function of given frequency and voltage of the plasma. And you can see that density changes and could drastically increase factor 3. So, and so what we try to understand is what makes the difference. And again, Sarvish will tell you that this large peak is due to so-called electron bounce resonance. This is not electron cyclotron resonance. It's a factor of 2 different. And again, kind of surprised us that this is relatively basic effect was not described before. So it was experimentally verified by Dalian group, which is shown on the right. Another kind of surprise was here. You can see this kind of small bump between 20 and 40 Gauss, and we try to understand what it is. And again, I'll tell you a secret. We thought that Bernstein wave should be excited in this discharge, and I had a student who looked at it and couldn't find it. And after 8 years of searching, finally Savish and his group found that indeed in this range you excite Bernstein waves, and he'll explain why. Okay, I'll skip this. Yeah, so if, he'll show, maybe I'll show, yeah, this is just one more point and I'll finish. So for inductive discharge, you have a similar effect. So what you see here, it's plasma density as plasma power in inductively coupled discharge, and it shows this transition from capacitive to inductive mode, where distribution function, which is shown on the right, which is measured distribution, it drastically changes. And so what we did, we upgraded our code to have a simulation of inductive discharge. So for that, you need electromagnetics. If you do it just straightforward using explicit and E scheme, you're very limited by time step. So it doesn't work. So what you have to do, you have to remove radiation so you can really increase the time step. And so that's what was done in our recent paper. And we upgraded the code, and with that, we can simulate distribution function, and you can see that you have some kind of a big loss cone in distribution function, and you can understand that. We also work on understanding skin effect, and this is in our recent papers, maybe last movie, and I already showed you rotating magnetic field, and so I'll show you how it looks heating with inductive discharge with rotating magnetic field, and you can see that you can simulate this complicated phenomena where inductive field and magnetic rotates, and you produce a complicated turbulence, as you can see in density plots and potential. And I'll probably finish here. So we have codes, so we simulated discharges. Sorry. And I'll take questions. So
Hello. Okay.
forgot
Thank
my
you.
conclusions. Anyway, so yeah, I finished the questions.
Okay. So thank you, Professor. So I'm going to take some questions. So you have covered mostly a lot of things, interesting things from low temperature perspective, and now the floor is open for questions from the audience. So if you have any questions, please. Are you able to hear?
Yeah, yeah, I can hear you. At least I can hear.
Yes. So please raise your hand. Okay. So if you have any questions, you can actually put it down, and then we can also mail to him, and we can get it. Okay. So regarding that magnetic field that you applied parallel to the transverse to the CCP. So do you think that is practically I think realizable in a really semiconductor industry like where?
Right. So what I showed you is a magnetically enhanced. It's actually patterned by IBM and also by Applied. So what's used in real reactors? Honestly, I don't know. It's a big secret. If they use it or not, I have no way of saying. Right? It's a black box, right? When they sell the plasma reactors, they don't tell you anything.
Okay, yeah. So that is very interesting. We also do some kind of electron beam discharges, and you also showed some interesting results from that end. Um, so I think uh, yeah. So this thing that you talked about was like this kind of instabilities that arises when you have the electric field that is generated self-consistently when you have different ion electron mass so across the magnetic field, so you have some radial electric field that is created. So the electrons are magnetized in the center, and then you have an electric field that creates, and that results in E cross B drift. So does it depend on the size of the dimensions of the plasma length?
Right. So this is my 1 minute story, right? So indeed, it very much depends if ions are magnetized or not. So with a large linear machine, instabilities could be somewhat different. In smaller machines where ions are not magnetized, it's typically Simon Hoare. So linear theory have been developed, but nonlinear theory, how stability saturates and what kind of turbulence it produces, very little was understood.
Okay, so I think we are not having. So we are going to close this session. Thank you so much, Professor.
Okay.
So thank you very much.
You're
Okay,
welcome. Bye.
bye.